This one is a pendulum problem, so we're going to have to use work energy to solve it. I'll start with the diagram. We have a pendulum that makes a 55-degree angle with the vertical. It has a length L, and this length also is L, and starts off at some height H, travels along some kind of arc here to get to the bottom. So there's our mass here and here. Now, the little trick with pendulums, of course, is that this is a right triangle. So if I just consider this triangle here, that the side of the triangle is L cosine 55. Therefore, since the entire length of the pendulum is L, I know that L cosine 55 plus H is equal to L, so H is equal to L minus L cosine theta. I'm going to need that trick a little bit later. In this case, it's a 4.5 meter long vine, and the initial angle is 55. So the height through which the monkey swings is 1.92 meters. Okay, so for part A, it's just a simple work energy problem. We want to know how fast the monkey is traveling at the lowest point of the motion. So the forces involved are mg and tension. And tension does no work because the tension force is always perpendicular to delta S, right? The tension force points radially along the circular motion, and the tension force is tangential. At every point in the circle, the displacement vector points tangent to the circle, the tension vector points radially to the circle, so they are always by definition perpendicular, so the tension does no work. Gravity does positive mgh of work because it goes down, right? The initial potential energy up here is mgh. The final potential energy down here is 0, so if you take the difference and minus that difference is positive mgh. So that works out to be 282.2 joules. Okay, so we sum the work done by all forces. That's equal to 282. That's equal to the change in kinetic energy. Now, in this case, we have to be a little careful here because the monkey does start off with an initial velocity. So this is 282.2 is equal to 1/2 times 15 times v squared minus 1/2 times 15 times 3.5 squared. So if you work this out, you get 374.1 is equal to 7.5 v squared, so v is equal to 7.1 meters per second. So there's our answer for part A. There's the final velocity at the bottom of the motion. For part B, it says we'll assume the monkey's final speed is only 85% of what we calculated in part A, so that means the final velocity is 6.0. And we need to find out how much work is done by friction, right? So the work done by kinetic friction, we cannot use F delta S cosine theta because we have no idea what F is, we have no idea what delta S is, and we don't really know what theta is, to be honest. So that's not a good approach. Instead, we'll use the approach where the sum of the works is equal to the change in kinetic energy. And we know the work done by tension, we know the work done by gravity, and we know delta K in this case. Right? The work done by tension is still 0. The work done by gravity is still 282.2. And the change in kinetic energy can be calculated because the final kinetic energy depends on 6 squared, and the initial kinetic energy depends on 3.5 squared. So 282.2 plus the work done by friction is equal to 178.1. Okay, and so the work done by friction, I guess I got to round this off to two significant figures, don't I? So it's 100 joules. minus 100, sorry. Better be negative. Friction does negative work every time. Okay, that's it.